There's something profoundly unsettling about black holes, something that violates our deepest intuitions about the universe and about the possibility of escape, freedom, and survival. We're used to thinking that with sufficient effort, sufficient energy, sufficient cleverness, we can escape from anything, from gravity wells, from dangerous situations, from constraints of all kinds. Build a powerful enough rocket and you can escape Earth's gravity. Travel fast enough and you can outrun pursuit. Apply enough force and you can break free from bonds. But black holes are different. Black holes represent absolute imprisonment, inescapable confinement, a region of space-time from which nothing, not matter, not light, not information, not anything can escape once it crosses a certain boundary. This boundary is called the event horizon, and it's the defining feature of black holes, the point of no return, beyond which all trajectories lead inexorably inward toward the singularity at the center. Not even light survives. Photons, traveling at the universe's speed limit, cannot escape from within the event horizon. They're pulled back by gravity, so extreme that space-time itself is curved into a trap, a one-way surface, through which things can fall, but from which nothing can emerge. And if light cannot escape, if the fastest thing in the universe, the thing that defines the cosmic speed limit, is trapped, then nothing else can escape either. Nothing slower than light, nothing with mass, nothing with any physical properties whatsoever. The event horizon is an absolute barrier, not in the sense of a wall you might break through with sufficient force, but in the sense of a geometric property of space-time that makes escape literally impossible, not just difficult, but forbidden by the structure of reality itself. And I want to explain why this is true, why the impossibility of escape from black holes is not just a limitation of current technology or current understanding, but a fundamental consequence of general relativity, of the nature of space-time, of how gravity works when taken to its extreme. I want to explore what happens at and beyond the event horizon, why escape is impossible, what this means for anything that falls in, and why even apparent exceptions, Hawking radiation, quantum tunneling, wormholes don't actually allow escape in any meaningful sense. Let me start with the basics of what a black hole is and why it forms, because understanding the origin helps clarify why escape is impossible. A black hole forms when matter is compressed to such extreme density that its gravity becomes so strong that space-time curves back on itself, creating a region from which light cannot escape. This happens when massive stars, those many times more massive than the Sun, exhaust their nuclear fuel and can no longer support themselves against gravitational collapse. The core collapses catastrophically, compressing to extraordinary density. And if the mass is sufficient, roughly 3 times the Sun's mass or more, nothing can stop the collapse. No known force or pressure can resist the gravitational pull. The collapse continues to a point of infinite density, a singularity, surrounded by an event horizon whose size depends on the mass. For a non-rotating black hole, the event horizon radius, called the Schwarzschild radius, is res equals 2gm divided by c squared, where g is the gravitational constant, m is the black hole's mass, and c is the speed of light. For a black hole with the Sun's mass, the Schwarzschild radius is about 3 kilometers. For a black hole with 1 million solar masses, typical of supermassive black holes at galaxy centers, the radius is about 3 million kilometers, roughly 4 times the Sun's radius. So black holes can be small, stellar mass black holes with radii of kilometers, or enormous supermassive black holes with radii larger than planetary orbits. But regardless of size, they all share the defining property, an event horizon from which escape is impossible. Now, why is escape impossible? The answer requires understanding how gravity works. According to general relativity, Einstein's theory of gravity is curved space-time. In Newton's theory, gravity is a force. Masses attract each other through gravitational force, proportional to their masses, and inversely proportional to the square of the distance between them. In this picture, escape is about energy. If you give an object enough kinetic energy through sufficient velocity, it can overcome gravitational attraction and escape to infinity. The escape velocity is the minimum velocity needed to escape, and it increases with mass and decreases with distance. For Earth, escape velocity is about 11 kilometers per second. For a neutron star, it might be 100,000 kilometers per second or more. For a black hole, Newtonian theory would predict escape velocity greater than the speed of light at distances closer than the Schwarzschild radius. But general relativity fundamentally changes this picture. Gravity isn't a force in general relativity, it's the curvature of space-time caused by mass and energy. Massive objects curve space-time around them, and objects move along geodesics, the straightest possible paths, through this curved space-time. What we perceive as gravitational attraction is actually objects following curved paths through curved space-time. And crucially, the speed of light is a universal constant. Nothing can travel faster than light, not through additional energy, not through any means. Light itself travels along null geodesics paths through space-time that are neither time-like slower than light, nor space-like faster than light would need to be, but exactly at the boundary. So when gravity is strong enough that escape would require exceeding the speed of light, escape becomes impossible, not difficult, not requiring enormous energy, but literally impossible, because it would require violating the fundamental speed limits of the universe. This is what happens at the event horizon of a black hole. At the event horizon, the curvature of space-time is such that all future directed paths, all possible trajectories forward in time point inward toward the singularity. There are no future directed paths pointing outward. To escape, you would need to follow a path that goes outward, but all such paths are space-like. They would require traveling faster than light, which is impossible. So escape from beyond the event horizon is not a matter of having insufficient energy or insufficient velocity. It's a matter of there being no possible trajectory, no path through space-time that leads outward. The geometry of space-time itself forbids it. It's like asking whether you can travel into the past. It's not that you lack the technology or the energy. It's that the structure of space-time in standard general relativity, without closed time-like curves, doesn't permit it. Now, let me make this more precise by describing what actually happens to space-time at and near the event horizon. Far from the black hole, space-time is approximately flat curved, slightly by the black hole's mass, but not dramatically. As you approach the black hole, space-time curvature increases. At the event horizon, something remarkable happens. The roles of space and time switch, in a sense. Let me explain what this means. In normal space-time, far from gravitating bodies, time is a dimension you must move forward through. You can't avoid moving into the future, can't stop or reverse temporal motion. Space is dimensions you can move through in any direction. You can go north or south, east or west, up or down, and your choices about spatial motion are classically free. But at the event horizon, the radial direction toward or away from the singularity becomes time-like. It becomes a direction you must move through, specifically inward. Just as you must move forward in time, in normal space-time, at and inside the event horizon, you must move inward in radius. And time becomes space-like in a certain sense. It's no longer the direction of inevitable motion, but rather a dimension with more freedom. This is a complicated and somewhat misleading way to describe it, because coordinates become pathological at the horizon, but the key point is, inside the event horizon, moving toward the singularity is not a choice or a matter of trajectory. It's inevitable, built into the structure of space-time. As inevitable as moving forward in time is for us outside. So asking why can't you escape from inside the event horizon is like asking Why can't you avoid moving into the future? The answer is the same, because the geometry of space-time doesn't permit it. Future-directed paths necessarily lead inward, toward the singularity, just as in normal space-time, future-directed paths necessarily lead forward in time. Now you might object, but can't you fire rockets, accelerate outward, fight against the inward motion? And the answer is you can fire rockets, you can accelerate, but all this does is change your path within the constrained space of possibilities. You can't create a path that leads outward because no such paths exist as solutions to the equations of motion in this geometry. It's like being on a river flowing toward a waterfall. Far from the waterfall, you can paddle upstream and escape. Near the waterfall, the current becomes stronger and you must paddle harder. At some point, the equivalent of the event horizon, the current, exceeds any speed you can achieve, and you inevitably go over the waterfall regardless of how hard you paddle. But actually, this analogy is too weak because it suggests that with a faster boat you could still escape. The black hole situation is more absolute. It's not that the current exceeds your maximum speed, it's that all directions lead inward. There is no upstream direction to paddle in. Every direction is downstream toward the singularity. Space itself is structured such that outward paths don't exist as future-directed trajectories. So escape is impossible, not because you lack power, but because the concept of outward has become inconsistent with forward in time inside the event horizon. Now, let me turn to what happens to objects and observers as they approach and cross the event horizon, because the impossibility of escape manifests in observable, or rather unobservable ways. Suppose an astronaut falls toward a black hole. As they approach the event horizon from outside, several things happen from the perspective of a distant observer watching. The astronaut appears to slow down as they approach the horizon, taking longer and longer to cover each additional distance toward the horizon. This is gravitational time, dilation time. Near the black hole passes more slowly relative to time far away. The astronaut's light becomes increasingly red-shifted, stretched to longer wavelengths, shifting from visible to infrared to radio waves and beyond. This is gravitational redshift, a consequence of photons climbing out of the gravitational field and losing energy. The astronaut appears to freeze at the event horizon, asymptotically approaching, but never quite crossing in the distant observer's time frame, and their light becomes infinitely redshifted, fading to undetectability. From the distant observer's perspective, the astronaut never crosses the event horizon. They appear to freeze just outside, gradually fading from view as their light redshifts to undetectability, but never actually crossing. This is because light emitted from closer and closer to the horizon takes longer and longer to reach the distant observer, and light emitted exactly at the horizon takes infinite time to escape. It never escapes, it just asymptotically approaches the horizon from outside. But from the astronaut's perspective, something very different happens. They cross the event horizon in finite proper time, time as measured by their own clock, experiencing nothing unusual. At the moment of crossing for a supermassive black hole, for stellar mass black holes, tidal forces might be extreme even before crossing. Once inside, they continue falling inward toward the singularity, and this inward fall is inevitable. There's no stopping, no turning round, no escape. They have a finite time remaining until hitting the singularity. For a Schwarzschild black hole, the time from horizon to singularity is roughly p, where m is the mass, which is about 15 microseconds for a solar mass black hole, or about 4 hours for a billion solar mass black hole. As they approach the singularity, tidal forces, the difference in gravitational pull between their head and feet, increase without bound, stretching them and ultimately destroying them in a process called spaghettification. So the astronaut's experience is finite time to cross the horizon, finite time from horizon to singularity, inevitable destruction. but they can never send information about crossing or about conditions inside back to the outside. Any signals they send inward after crossing are trapped, moving toward the singularity along with them, never reaching the outside. This is the observational manifestation of the impossibility of escape. Once crossed, the event horizon is a one-way boundary. Information goes in but doesn't come out. Observers outside can never receive signals from inside. The interior is causally disconnected from the exterior events inside, cannot affect events outside. Now you might ask, if observers outside never see anything cross the horizon, if from their perspective objects freeze at the horizon, then in what sense does the interior exist, or does anything actually fall in? This is a deep question related to the nature of space-time and the interpretation of general relativity. The answer is that different reference frames, different perspectives give different descriptions of events, but all are valid within their domains. From the distant observer's frame, the infalling object asymptotically approaches the horizon but doesn't cross in finite coordinate time, time measured in the distant observer's coordinates. From the infalling object's frame, it crosses in finite proper time and reaches the singularity in finite proper time. Both descriptions are correct within general relativity. The distant frame breaks down at the horizon, the coordinates become singular, time appears to stop, but this is a coordinate singularity, not a physical singularity. Switching to coordinates adapted to the infalling observer, like Eddington-Finkelstein or Kruskal-Sekares coordinates, removes the coordinate singularity and shows that the horizon and interior are perfectly regular parts of space-time. So the interior does exist, objects do fall in and reach the singularity, all in finite proper time. But the causal structure is such that these events are unobservable from outside the exterior, and interior are distinct causal regions separated by the event horizon, which is a null surface, a surface that light travels along, separating them. Now, let me turn to an important question. Are there different kinds of black holes, and does the impossibility of escape depend on the black hole's properties? Black holes are characterized by just three properties: mass, electric charge, and angular momentum. The no-hair theorem says that black holes have no other distinguishing features. All information about the matter that collapsed to form the black hole is lost, except for these three quantities. Non-rotating, uncharged black holes are called Schwarzschild black holes, described by the Schwarzschild solution to Einstein's equations. These have a single event horizon at radius r's equals 2gm divided by c squared. Rotating black holes are called Kerr black holes. Rotation adds complexity. They have two horizons, an outer event horizon and an inner Cauchy horizon, an ergosphere region outside the event horizon where space-time itself is dragged around by the black hole's rotation, and different geometry. Charged black holes, Reisner-Nordstrom for non-rotating charged black holes, Kerr-Newman for rotating charged ones, also have more complex structure with two horizons. But crucially, all black holes share the fundamental property, an event horizon from which escape is impossible. The impossibility of escape is not specific to Schwarzschild black holes. It holds for Kerr black holes, for charged black holes, for any black hole configuration. In fact, the impossibility is even more fundamental. The event horizon is defined as the boundary of the region from which escape to infinity is impossible. So by definition, if there's an event horizon, escape from inside is impossible. However, some exotic solutions, naked singularities, wormholes, don't have event horizons, and their properties are different. But these are thought to be unphysical or unstable cosmic censorship. Conjectures suggest that singularities are always hidden behind event horizons, and traversable wormholes likely require exotic matter with negative energy density, which might not exist or might be unstable. So in all realistic black hole scenarios, The event horizon exists and escape from beyond it is impossible. Now let me address what is perhaps the most famous apparent exception to the impossibility of escape: Hawking radiation. In the 1970 seconds, Stephen Hawking showed, using quantum field theory in curved spacetime, that black holes are not perfectly black. They emit thermal radiation with a temperature inversely proportional to their mass. For stellar mass black holes, this Hawking radiation is extraordinarily faint, temperatures of nanokelvins, far colder than the cosmic microwave background. So these black holes absorb more radiation than they emit and grow rather than shrink. But for smaller black holes, the temperature is higher, temperature scales as 1m, and eventually the black hole radiates energy, loses mass, shrinks, heats up further in a runaway process, and ultimately evaporates completely in a final burst of radiation. This seems to violate the claim that nothing escapes from black holes if black holes emit radiation. Isn't something escaping? But Hawking radiation doesn't actually come from inside the event horizon. It's produced just outside the horizon through quantum effects, and it's these quantum effects I need to explain carefully. In quantum field theory, even empty space is not truly empty, but is filled with quantum fluctuations, virtual particle pairs constantly appearing and annihilating on timescales, so short they don't violate energy conservation through the metric uncertainty principle. Near a black hole's event horizon, these quantum fluctuations have an interesting effect. So we'd been discussing Hawking radiation and how quantum fluctuations near the event horizon create particle pairs. Let me explain this mechanism more carefully, because it's crucial for understanding why Hawking radiation doesn't actually represent escape from inside the black hole. The standard picture, though somewhat misleading, goes like this. Near the event horizon, quantum fluctuations create virtual particle-antiparticle pairs. Normally, these pairs would annihilate almost immediately, returning the borrowed energy to the vacuum. But near the horizon, something different can happen. One particle of the pair can fall into the black hole while the other escapes to infinity. The escaping particle becomes real radiation, Hawking radiation, while the infalling particle has negative energy relative to infinity. This negative energy reduces the black hole's mass, causing it to gradually evaporate. But notice what's happening here. The radiation that escapes is created outside the event horizon, not inside. The particle that becomes Hawking radiation never crossed the event horizon and then escaped. It was created outside and escaped from outside. The particle that falls in carries negative energy, reducing the black hole's mass, but it's the outside particle that we observe as radiation. So Hawking radiation is not an exception to the impossibility of escape from inside the horizon. Nothing is escaping from inside. Instead, quantum effects near the horizon create radiation outside that carries away energy, gradually diminishing the black hole. Moreover, the standard virtual particle picture is somewhat misleading. It's a heuristic that captures some features of the calculation but isn't quite accurate. A more precise description involves quantum field modes that are defined relative to the horizon, and the difference between how these modes appear to observers far from the black hole versus observers falling into it. The calculation shows that what appears as vacuum to an infalling observer appears as thermal radiation to a distant observer, and this radiation carries energy away from the black hole. But again, the radiation originates from the horizon region, not from deep inside the black hole. It's a consequence of the horizon's existence and the quantum properties of fields in curved spacetime, not an escape from the interior. Now, Hawking radiation does raise profound questions about information and about what happens to matter that falls into a black hole. If a black hole eventually evaporates completely through Hawking radiation, what happens to the information about the matter that fell in? This is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. According to quantum mechanics, Information is conserved, the quantum state evolves unitarily, meaning that in principle you can reconstruct earlier states from later states, that information about the past is preserved in the present. But if matter falls into a black hole, and the black hole later evaporates into thermal Hawking radiation that carries no information about what fell in thermal radiation, is maximally random, carrying no distinguishing information, then information seems to be destroyed, violating quantum mechanics. This paradox has driven decades of research into quantum gravity, holography, the nature of black hole interiors, and the relationship between gravity and quantum mechanics. Various solutions have been proposed. Information is somehow encoded in subtle correlations in the Hawking radiation that look thermal but actually carry information. This requires non-local quantum correlations that seem to violate causality. Information is preserved in remnants left after black hole evaporation, but these remnants would need to have infinite internal states, which seems problematic. Information escapes through modifications to the horizon structure, firewalls or other quantum corrections that change the classical picture, but these seem to violate the equivalence principle or other fundamental principles. The interior doesn't exist in the way we think. Perhaps it's a holographic projection or a quantum state that doesn't correspond to a classical space-time geometry. This is the direction suggested by AS, CFT, correspondence and holography. The information paradox remains unresolved, and I don't want to claim a definitive answer. But crucially, none of the proposed solutions involve classical escape from inside the event horizon. They all involve quantum effects, modifications to our understanding of space-time at the horizon, or fundamentally different ways of thinking about the interior. They don't change the fact that classical objects, spaceships, astronauts, light rays cannot escape from inside the horizon. The impossibility of classical escape remains absolute. Now let me turn to another apparent exception: quantum tunneling. In quantum mechanics, particles can tunnel through barriers that would be classically impenetrable, appearing on the other side with some probability, even though they don't have enough energy to classically overcome the barrier. Could quantum tunneling allow escape from a black hole? The short answer is no, for several reasons. First, quantum tunneling probabilities decrease exponentially with the height and width of the barrier and with the particle's mass. For macroscopic objects, or even for individual particles trying to tunnel across distances comparable to the Schwarzschild radius, the tunneling probability is so extraordinarily small, perhaps 10, negative 10, 70 or smaller, for realistic scenarios, that it's effectively zero. You could wait for times far longer than the age of the universe, and tunneling wouldn't occur. Second, tunneling assumes a potential barrier of the sort that appears in quantum mechanics, a region of higher potential energy that particles must cross. But the event horizon isn't a potential barrier in this sense. It's a geometric feature of space-time, a null surface separating causally disconnected regions. Quantum tunneling through potential barriers doesn't apply to tunneling through space-time geometry. Third, even if some form of quantum tunneling could occur, it would still respect causality and the light speed limit. Quantum tunneling doesn't allow faster-than-light travel particles tunnel through barriers, but don't propagate faster than light on average. So tunneling couldn't allow escape from a region where all future directed paths point inward. The geometric impossibility remains. So quantum tunneling is not a mechanism for escaping black holes. Quantum effects might modify the horizon structure in subtle ways, might lead to Hawking radiation, might eventually resolve the information paradox, but they don't permit classical escape through tunneling or other quantum processes. Now, let me address another speculative possibility: wormholes. Wormholes are hypothetical tunnels through space-time connecting two distant regions, potentially allowing travel between them without traversing the intervening space. Some solutions to Einstein's equations describe wormholes, and they appear in science fiction as shortcuts for interstellar travel or as connections between universes. Could a wormhole provide an escape route from inside a black hole? The answer depends on the type of wormhole and on whether traversable wormholes can exist. The Schwarzschild solution actually contains a wormhole. It describes not just a black hole, but also a connection to another asymptotically flat region of space-time, sometimes called a white hole. Mathematically, the full Schwarzschild geometry includes two exterior regions connected by a wormhole, with the black hole in one region and a white hole, the time-reversed black hole that nothing can enter in the other. But this wormhole is not traversable. If you fall into the black hole, you cannot reach the other exterior region. The wormhole throat collapses too quickly, and you hit the singularity before you can traverse the wormhole. The geometry allows a wormhole to exist, but only for an instant, and nothing can travel through it before it collapses. So the Schwarzschild wormhole doesn't provide an escape route. Rotating black holes, curved black holes, have more complex interiors with Cauchy horizons, ring singularities, and regions that are mathematically connected to other universes or other regions of space-time. In principle, if you could navigate the interior carefully, avoid the singularities, pass through the Cauchy horizon, you might reach these other regions. But there are several problems. The Cauchy horizon is unstable. Small perturbations cause it to become a singularity, destroying the inner structure. This is the mass inflation instability. Passing through the Cauchy horizon would expose you to infinite blue-shifted radiation from the entire external universe's history, which would likely destroy you. The trajectories that avoid singularities and reach the other regions might require impossible fine-tuning, and it's unclear if they're physically realizable. And even if you reach another region, it's not clear that region is the same universe you came from, or that it's a classical space-time rather than a quantum state or a mathematical artifact. So while rotating black holes have rich mathematical structure, they don't provide practical escape routes, and most physicists suspect that quantum effects or instabilities destroy the exotic internal structure, leaving just a singularity that anything falling in will inevitably hit. What about constructed wormholes, traversable wormholes that might be engineered or might exist naturally? The problem is that traversable wormholes require exotic matter with negative energy density to hold the throat open against collapse. The stress-energy tensor must violate energy conditions that are satisfied by all known classical matter. Quantum fields can have negative energy densities locally. The Casimir effect demonstrates this, but accumulating sufficient negative energy to stabilize a macroscopic wormhole is likely impossible, requires violating quantum inequalities that limit how much and how long negative energy can exist, or requires physics beyond the standard model and general relativity. So traversable wormholes are at best highly speculative, probably impossible, and certainly not a mechanism for escaping from existing black holes. They might be a way to avoid falling into a black hole in the first place if you could create a wormhole connecting 2 points outside black holes. You could travel between them, but they don't allow escape from inside event horizons. Now, let me turn to a different question. What does it mean to say nothing escapes? And are there edge cases or technicalities that qualify this statement? The strict statement is, from inside the event horizon, no future-directed time-like or null world-line trajectory can reach infinity, or even reach the exterior region outside the horizon. This means no object with mass, which follows time-like trajectories, can escape. No light, which follows null trajectories, can escape. And no signal or information can escape. Because signals propagate at or below the speed of light, this is absolute. It's a consequence of the causal structure of space-time, not a limitation of technology or energy. But there are some technicalities and edge cases to consider. Objects exactly at the event horizon, hovering there, are in an unstable position. They're not inside yet, so they can still escape in principle, but it would require infinite acceleration to hover there, which is impossible. So this is a mathematical edge case with no physical realization. For rotating black holes, the ergosphere A region, outside the event horizon, where space-time is dragged around by the black hole's rotation, allows interesting effects. Objects in the ergosphere can have negative energy relative to infinity, and through the Penrose process, energy can be extracted from a black hole's rotation, but this doesn't involve escape from inside the event horizon. It's a process occurring outside the horizon, extracting rotational energy, not mass energy, from inside. Hawking radiation, as discussed, originates outside the horizon and causes the black hole to evaporate, but nothing escapes from inside. If a black hole is surrounded by matter, an accretion disk, in falling gas, etc., some of this matter might be ejected in jets or outflows due to magnetic fields, radiation pressure, or other astrophysical processes. But again, this is matter that never crossed the horizon, being ejected from outside before falling in. So none of these edge cases or technicalities change the fundamental point from inside the event horizon. Escape is impossible. Now let me address what I think is one of the most profound implications of the impossibility of escape, what it means for the fate of anything that falls into a black hole, and whether we can even meaningfully talk about the interior, given that it's causally disconnected from the exterior. When matter crosses the event horizon and falls toward the singularity, what happens to it? In classical general relativity, the answer is stark. The matter is destroyed at the singularity, where space-time curvature becomes infinite, where tidal forces become infinite, where the classical description breaks down completely. The singularity is not a place or a time, it's a boundary to space-time where geodesics particle trajectories terminate, where the geometry becomes pathological, where the equations of general relativity no longer give meaningful answers. What happens at the singularity is unknown because general relativity predicts its own breakdown there. The curvature becomes so extreme that quantum effects of gravity become important, and we need a theory of quantum gravity to describe what actually occurs. Does the matter that hits the singularity get compressed to infinite density? Does it transition to some quantum state? Does it tunnel to another region of space-time? We don't know, and without a theory of quantum gravity, we can't calculate it. But regardless of what happens at the singularity, the key point is that matter crossing the horizon cannot escape back to the exterior. Its future is confined to the region inside the horizon, terminating at the singularity, or at whatever quantum gravity replaces the singularity. This raises the question, if the interior is causally disconnected from the exterior, if nothing inside can affect anything outside, does the interior exist in any meaningful sense for exterior observers? This is a deep question touching on the nature of existence and the interpretation of general relativity. One view is that the interior exists as part of space-time, as a region described by the equations of general relativity, even though it's not observable from outside. Observers who fall in experience the interior, measure its properties, hit the singularity, all in finite proper time. The interior is as real as the exterior, just causally disconnected from it. Another view, suggested by some approaches to quantum gravity and holography, is that the interior might not exist as an independent region of space-time, but might be a kind of holographic projection or quantum state associated with the horizon. In ADS, CFT correspondence, a specific realization of holographic principle, black holes in anti-de Sitter space are described by quantum states in a lower dimensional boundary theory, and the black hole interior might be an emergent feature, of this quantum state rather than a fundamental geometric region. If this view is correct, and its applicability to realistic black holes is uncertain, then the interior's existence is different from our classical intuition. It's not a region you can point to as separate from the exterior, but rather an aspect of the quantum state describing the whole system. But even in this view, observers falling in would experience something. Their world lines don't just end at the horizon. What they experience might be described as entering the interior, even if the fundamental description doesn't include a separate interior region. So the question of whether the interior exists is subtle and depends on interpretation and on quantum gravity, which we don't fully understand. But for classical physics and for the experience of infalling observers, the interior is real and escape from it is impossible. Now, let me turn to what might be the most disturbing aspect of the impossibility of escape: the implications for information, determinism, and the predictability of physics. In classical general relativity, black holes destroy information. Matter falling in carries information about its composition, its quantum state, its history. Once inside the horizon, this information is inaccessible to exterior observers. If the black hole evaporates via Hawking radiation, the information seems to be lost. The radiation is thermal, carrying no distinguishing features, no trace of what fell in. This loss of information violates quantum mechanics, which requires that information be preserved, that quantum evolution be unitary, reversible in principle. The information paradox, as mentioned earlier, remains unresolved, but its existence highlights a deep tension between general relativity and quantum mechanics regarding black holes. If information is truly lost, then quantum mechanics is violated, determinism is broken, and physics becomes fundamentally unpredictable. You cannot reconstruct the past from the present because information about the past has been destroyed in black holes. If information is preserved, then either Hawking radiation carries subtle information in ways we don't yet understand, or the black hole interior is more complex than we think, or our entire picture of space-time and horizons is wrong at some level. This is not just an academic puzzle, it's a fundamental question about the nature of physical law. Most physicists believe information must be preserved because giving up unitarity would undermine quantum mechanics, which is extraordinarily well tested. But how information escapes or is preserved is unknown. Recent progress suggests that quantum entanglement between Hawking radiation and the black hole might carry information that the radiation is not truly thermal but has subtle correlations that encode information. Or perhaps information is somehow stored on the horizon. The holographic principle suggests that the information content of a region is proportional to its boundary area rather than its volume, and the horizon's area might encode all information about what fell in. But these ideas require quantum gravity to fully formulate, and they don't change the classical impossibility of escape. They're quantum effects that might resolve the information paradox without permitting classical objects to escape from inside the horizon. So the impossibility of escape creates a profound conflict between general relativity and quantum mechanics, a conflict that reveals the incompleteness of our current theories and that points toward the need for quantum gravity. Now, let me address one more question. Are there astrophysical or observational consequences of the impossibility of escape? Ways that we can confirm that black holes really do have event horizons from which nothing escapes? We can't directly observe event horizons. They're defined by causal structure, not by emitting or reflecting light. But we can observe effects consistent with event horizons existing. So we'd been discussing observational evidence for event horizons, and I want to continue by exploring what we can and cannot observe about black holes and why the impossibility of escape manifests in what we see, or rather, what we don't see. Astronomers have observed numerous black hole candidates objects with masses too large to be neutron stars, compact enough that their gravitational effects match what we'd expect from black holes, and most tellingly, dark in ways that suggest event horizons. The observational signatures of black holes include X-ray emissions from accretion disks, matter spiraling into the black hole heats to millions of degrees through friction and compression, emitting intense X-rays before crossing the horizon. The abrupt cutoff in emission at small radii, consistent with matter crossing an event horizon and disappearing, rather than hitting a surface that would emit additional radiation. Gravitational wave detections from black hole mergers, LIGO, and other detectors have observed dozens of black hole collision events, where the waveforms match precisely the predictions of general relativity for black holes, with event horizons merging, forming larger black holes and settling down through ring-down oscillations. Imaging of black hole shadows. The Event Horizon Telescope imaged the supermassive black hole in galaxy M87, showing a dark region, the shadow, surrounded by bright emission from the accretion disk. The size and shape of the shadow match predictions for a black hole with an event horizon. Stellar orbits around Sagittarius, A*. The supermassive black hole at the Milky Way center stars orbit extraordinarily fast. Their orbital velocities and periods indicate a central mass of about 4 million solar masses concentrated in a region smaller than the solar system. No known object other than a black hole could have such extreme density. All of this evidence is consistent with black holes having event horizons, regions from which light doesn't escape, causing the central darkness we observe. But crucially, we can't observe the event horizon itself. We observe its effects, the boundary where emission stops, where objects disappear from view. And we can't observe the interior. Everything inside is hidden from us, inaccessible to observation, causally disconnected. This observational inaccessibility is itself evidence for the impossibility of escape. If objects could escape from inside the horizon, we would observe them: light escaping, matter being ejected, signals from the interior. The fact that we observe nothing from inside, that regions beyond a certain radius are completely dark, is exactly what the impossibility of escape predicts. Now, some alternative theories propose objects that mimic black holes but don't have true event horizons. These are called black hole mimickers or horizonless compact objects. Examples include gravastars, hypothetical objects where quantum effects prevent horizon formation, boson stars, exotic configurations of bosonic fields, or ultra-compact neutron stars just barely avoiding collapse to black holes. These objects might have surfaces just outside where the event horizon would form, and they might emit slight amounts of radiation from their surfaces, distinguishable in principle from true black holes. So far, observations are consistent with true black holes with event horizons, not with mimickers. The shadows we observe are as dark as expected for event horizons. The ring-down waveforms from mergers match black holes, not other configurations. The absence of surface emission is consistent with horizons, not surfaces. But observations have limited precision, and we can't completely rule out that some objects we call black holes might be exotic alternatives. However, even if some compact objects are mimickers, the most massive and most extreme cases, supermassive black holes, the stellar remnants from the most massive star collapses, almost certainly are true black holes with event horizons, because no known physics can support such masses against collapse without forming horizons. So observationally, we have strong evidence for event horizons and for the impossibility of escape they imply, though we can't observe horizons directly or peer inside to see what happens there. Now let me turn to what I think is perhaps the most profound philosophical implication of the impossibility of escape from black holes. What it tells us about the nature of physical law, about boundaries and limits, about the existence of absolute barriers in the universe. We're used to thinking that physical laws describe how things behave, what's possible, what's forbidden. But usually, forbidden means requires infinite energy or violates conservation laws or is statistically improbable. There's a sense in which forbidden things are limits we approach but never quite reach, or barriers we could overcome with sufficient resources. But the event horizon represents a different kind of barrier, a geometric, absolute, inescapable boundary. It's not that escaping from inside would require infinite energy, though it would. It's that escape is geometrically impossible. There exist no trajectories, no paths through space-time that lead from inside to outside while moving forward in time. The impossibility is built into the structure of space-time itself, into the causal relationships between events, into the very fabric of reality as described by general relativity. This is different from other impossibilities in physics. You can't travel faster than light, but this is a limit you approach asymptotically. You can always go faster than you're currently going by adding more energy. You just can't reach or exceed light speed. You can't violate conservation of energy, but this is a constraint on processes, not a geometric barrier. You can imagine violating it, even if it doesn't happen. But you can't escape from inside an event horizon in the same way that you can't make 2 + 2 = 5 or make a triangle's angles sum to more than 180 degrees in flat geometry. It's not a physical limitation, but a logical consequence of the structure you're embedded in. So black holes teach us that the universe contains absolute barriers, regions beyond which no causal influence can reach, boundaries that cannot be crossed in certain directions regardless of technology or effort. And this absoluteness is both fascinating and terrifying. It reveals that reality has hard limits, inescapable constraints, regions fundamentally beyond our reach. Now let me address what might be the most important question of all. Given that escape is impossible, what does this mean for the ultimate fate of anything that falls into a black hole? And what does it mean for the black hole's own fate? For the infalling object, a star, a planet, a spacecraft, a person, the fate is obliteration. As you fall toward the singularity, tidal forces increase. These are differential gravitational forces. Gravity is stronger, closer to the singularity. So your feet, if falling feet first, are pulled more strongly than your head, stretching you vertically. Simultaneously, you're compressed horizontally, because radial geodesics, straight line paths in curved space-time, converge toward the singularity. The stretching and compression increase without bound as you approach the singularity. For stellar mass black holes with small Schwarzschild radii, tidal forces become extreme before you even reach the horizon. You'd be torn apart outside the horizon. For supermassive black holes with large Schwarzschild radii, tidal forces at the horizon are mild and you could cross comfortably. But as you fall inward toward the singularity, tidal forces eventually become extreme, regardless of the black hole's size. At some point, the tidal forces exceed the molecular or atomic binding energies holding you together, and you're torn apart into molecules, then atoms, then subatomic particles. The process is sometimes called spaghettification. You're stretched into a long, thin strand and eventually ripped apart completely. The time from horizon to singularity is finite and short microseconds for stellar mass black holes, hours for supermassive black holes. In this time, you're stretched, torn apart, and ultimately reach the singularity where classical general relativity breaks down and we don't know what happens. Quantum gravity might replace the classical singularity with something else, a quantum bounce, a transition to another region of space-time, a quantum state that doesn't correspond to classical geometry, but we don't know. What we do know is that you cannot escape, cannot avoid the singularity once inside the horizon, cannot survive the tidal forces, and cannot send any information about your fate back to the outside universe. You are lost completely and irrevocably from the perspective of anyone outside. For the black hole itself, the fate depends on Hawking radiation and on the universe's expansion. If the black hole is more massive than a few tens of solar masses, it's currently gaining mass from the cosmic microwave background faster than it's losing mass to Hawking radiation. It's growing, not shrinking. But as the universe expands and cools, the cosmic microwave background temperature drops, and eventually even massive black holes will begin to lose mass through Hawking radiation. The evaporation timescale is extraordinarily long, proportional to the cube of the mass. For a solar mass black hole, evaporation takes about 1067 years. For a supermassive black hole of 1 billion solar masses, evaporation takes about 10,100 years. These timescales are unimaginably long, vastly longer than the current age of the universe, 10 years. Longer than the time until the last stars burn out, 14 years. Longer than proton decay timescales, if protons decay 35 years or more. But eventually, given infinite time or something approaching it, black holes evaporate completely, ending in a final burst of radiation and leaving behind what? If information is preserved, the final radiation carries away all the information about what fell in, encoded in subtle quantum correlations. If information is lost, the black hole disappears and the information is gone from the universe permanently. If remnants are left behind, there are tiny, stable or metastable objects containing the information. We don't know which scenario is correct because we don't have a complete theory of quantum gravity to calculate the final stages of evaporation. But regardless of details, the ultimate fate of black holes is evaporation, and the ultimate fate of anything that fell in is either information dispersed into radiation, or information lost, or information stored in remnants, but never escaped from the black hole in the form it entered. So the impossibility of escape is permanent and complete. Not only can nothing escape from inside the horizon, but the very structure that traps it eventually evaporates, destroying or dispersing whatever fell in without ever releasing it in its original form. Now let me turn to one final question that I think brings together everything we've discussed. What does the impossibility of escape from black holes teach us about the nature of the universe, about the limits of knowledge, and about the existence of boundaries beyond which we cannot go? Black holes are the universe's ultimate boundaries, regions that exist within our universe, that we can observe indirectly, that we can study mathematically, but that we cannot enter and return from, cannot communicate with, cannot rescue anything from. They represent absolute limits to exploration, to knowledge, to control. We cannot know directly what happens inside an event horizon because any observer who goes inside to investigate can never report back. We can calculate, can solve equations, can make predictions about the interior using general relativity and quantum field theory. But we cannot verify these predictions observationally because observation requires information to travel from the interior to exterior observers, and such information flow is impossible. This creates a fundamental limit to empirical science when applied to black hole interiors. We can have theories, but we cannot test them against observations of the interior. We can have confidence in our theories if they're based on well-tested principles, general relativity and appropriate regimes, quantum mechanics, thermodynamics, but we cannot achieve the same level of empirical confirmation we have for phenomena in the observable universe. And this limit is not temporary, not waiting for better technology. It's permanent and built into the causal structure of space-time. No future technology can send signals from inside a black hole to outside. No cleverness can overcome the geometric impossibility. So black holes represent regions about which we can never have complete empirical knowledge, regions that remain partially mysterious, regardless of how advanced our civilization becomes. This might seem like a defeat for science, an admission that some things are unknowable. But I think it's actually a profound insight into the structure of reality and into the relationship between knowledge and the universe. The universe contains boundaries, not just practical boundaries like distance or energy limits, but fundamental boundaries built into space-time structure. These boundaries divide the universe into causally disconnected regions. Some regions we can observe and study, others, like the interiors of black holes, or regions beyond our cosmic horizon in an expanding universe, are forever beyond observational reach. But recognizing these boundaries doesn't mean giving up on knowledge. It means understanding the scope and limits of different kinds of knowledge. We can have theoretical knowledge about black hole interiors, knowledge based on mathematical deduction from principles we trust. We can have observational knowledge about black hole exteriors, knowledge based on measurements of gravitational effects, radiation, shadows, orbits, and we can recognize that these two kinds of knowledge are different, that they have different degrees of certainty. That theoretical knowledge about unobservable regions is more tentative than empirical knowledge about observable phenomena. This recognition of limits is itself a form of knowledge, knowing what we can know and what we cannot know, understanding where observation ends and extrapolation begins, being honest about uncertainties and about regions beyond empirical reach. Moreover, the impossibility of escape from black holes teaches us something profound about physical law, that the universe has absolute constraints, inescapable limits, boundaries that cannot be crossed in certain directions. These constraints are not arbitrary or contingent, but are consequences of deep principles, the speed of light limit, the equivalence principle, the causal structure of space-time. They tell us that reality has a structure, that this structure has implications, and that some implications are absolute restrictions on what's possible. We're used to thinking that with sufficient ingenuity and resources, we can overcome any obstacle, can achieve any goal, can solve any problem. But black holes teach us otherwise. They teach us that some barriers are absolute, that some regions are genuinely beyond reach, that some fates are inescapable once certain thresholds are crossed. This is a humbling lesson, perhaps a disturbing one, but it's also a realistic one. It's a recognition that we're embedded in a universe with structure and laws that constrain what's possible, that we're subject to these constraints regardless of our desires or efforts, that reality is indifferent to our wishes and operates according to principles that sometimes create inescapable situations. And paradoxically, this recognition of limits can be liberating. If we accept that some things are impossible, we can stop wasting effort on the impossible and focus on what's actually achievable. If we accept that some regions are beyond reach, we can appreciate the regions we do have access to. If we accept that escape from black holes is impossible, we can focus on avoiding black holes, on understanding them from outside, on learning what we can learn without needing to venture inside. So the impossibility of escape from black holes is not just a technical fact about general relativity or a curious feature of extreme gravity. It's a fundamental statement about the nature of reality, about the existence of absolute boundaries, about the limits of knowledge and control, about our place in a universe that contains regions forever beyond our reach. Not even light survives inside an event horizon. Photons, travelling at the maximum possible speed, following null geodesics through space-time, cannot escape from within the horizon. They're trapped as completely as any massive object, as any spacecraft or signal or information. The horizon is a one-way boundary through which light can enter, but from which it cannot exit. And if light cannot escape, then nothing can escape. Nothing faster exists. No loophole permits what light cannot do. No cleverness overcomes what geometry forbids. This is the ultimate lesson of black holes, that the universe contains absolute traps, regions from which there is no escape, boundaries beyond which all paths lead to destruction. It's a terrifying lesson in some ways. It reveals that the universe has no obligation to provide escape routes, that some situations have no solutions, that some boundaries cannot be crossed back across. But it's also a profound lesson about physical law, about the consistency and absoluteness of natural principles, about the geometric nature of space-time, about the deep connections between causality and geometry that Einstein's general relativity revealed. Black holes exist because gravity is the curvature of space-time, because mass and energy curve space-time, and because sufficient curvature creates regions from which light cannot escape. They're not exotic add-ons to the universe, but inevitable consequences of taking gravity seriously, of understanding that space-time is dynamical and can be warped by matter and energy. And the impossibility of escape is not a failure of imagination or technology, but a logical consequence of the causal structure that curved space-time creates. When we say nothing can escape from a black hole, we're not making a claim about current limitations or technological barriers. We're stating a geometric fact about the universe's structure, a consequence of how space-time works, an implication of the deepest laws of physics we know. And this fact stands robust against speculation about quantum tunneling or wormholes or exotic physics, because it's grounded in principles we have every reason to trust: the speed of light, limit, the causal structure of space-time, the way gravity curves geometry. Could we be wrong? Could there be exceptions we haven't discovered? In science, we must always allow for the possibility of being wrong, of new discoveries overturning old understanding. But the impossibility of escape from black holes is as well established as almost any result in physics. It's a prediction of general relativity, which has been tested extensively and passed every test. It's consistent with all observations of black holes. It's required by the causal structure that underlies not just general relativity, but any theory that respects locality and the speed of light limit. So while we must remain open to new physics, we should recognize that overturning the impossibility of escape would require overturning some of the deepest and best confirmed principles in physics. It's not impossible, but it would be as revolutionary as discovering that energy isn't conserved or that logic doesn't apply to physical reality. Until and unless such revolutionary discoveries occur, we should accept what general relativity tells us: that black holes have event horizons, that these horizons are one-way boundaries, that nothing can escape from inside them, and that this impossibility is absolute, geometric, and inescapable. Not even light survives. And if light, the fastest thing in the universe, travelling along the straightest possible paths through space-time, cannot escape, then nothing else can either. The event horizon is the final barrier, the ultimate boundary, the point beyond which all trajectories lead to destruction and from which no return is possible. This is the profound truth about black holes, that general relativity reveals that the universe contains regions of absolute imprisonment, that gravity can create geometric traps from which nothing escapes, that space-time structure itself can forbid what seems merely difficult. And understanding this, accepting it, grappling with its implications is essential for understanding gravity, understanding space-time, and understanding our place in a universe that contains both the possibility of exploration and the existence of absolute boundaries beyond which exploration cannot go. Black holes are where the possible ends and the impossible begins, where the boundary between reachable and unreachable is written into the geometry of space-time itself, where not even light survives to tell the tale of what lies beyond. And that boundary stands absolute, inescapable, eternal as one of the universe's deepest truths.